So, like I said, slope fields are representations of the derivative as fields of slope. So we are going to actually learn today how to draw slope fields. And again, I actually tutored and kind of learned a new way that the PT teacher does it. And I was like, I really like that. Because it was like a table and it was super organized. And in years past, I had a table, but it was like not as neatly organized. So I'm going to show you my old way and I'm going to show you the new way. So again, still myself getting comfortable with like teaching that new way. But I think for those of you that think logically and think in tables, you're going to be like, I really like this. And I think if you're just like one of those people who are like scattered, then you're like, yeah, it doesn't work. But I like, like, my closet is Roy G. Biv. My children's closets are Roy G. Biv. Like, I like fluid. Although my 8-year-olds are hanging up the shirts and they are no longer Roy G. Biv. So I'm slightly excited. Okay. So yesterday, again, we did all the differentials. We worked through that. So today we're going to talk about slope fields and families of functions. So I gave you a blank graph, and it says to graph the family of functions that solve the differential equation dy dx equals cosine x. So you wanted to graph its original function. So the original function of dy equals cosine x dx is sine x. But it's not just sine x, it's sine x plus c. So again, it directly relates almost to last night's homework where we talked about all our answers had plus c's and we didn't know what c was. But you had to pick the equation that it could be. Because the derivative of c is 0, so c can be anything. And that's what these three graphs are saying. The middle graph in black is if c is 0. So that is the original sine x function. The purple graph and the green graph is if you shifted the sine function up or down. And that's the only transformation that c is going to do. So a plus c at the end of an equation is a phase shift up or down. Our graphs are not going to be shifted any other way with the c value. But c value will always manipulate my graph up or down. So then what we're going to do is we're going to take this idea of the cosine being the rate of change and the sine being the original function, and we're going to answer the questions related to that. Oh, I almost picked up yesterday's coffee and drink. All right. So the first question is about the slopes. And it's easier for you because you can see your graph as we talk through this. So it says, since the cosine of x is 0 at odd multiples of pi halves. So again, that should make sense. One is the cosine 0, the cosine is 0 at odd multiples of pi halves. That would mean that the slope is 0 at these odd multiples. So now what I want you to do is go back to that sine graph and investigate pi halves. So pi halves is going to be in here between 0 and pi, correct? And if you look at pi halves, and you look at all of the slopes at pi-halves, what are all of the slopes of the sine of x at pi-halves? 0. What's another way of saying the slope is 0? What else can we call those? We call them, yes, perfect. So a horizontal tangent is an implication that the slope is 0. So we have horizontal tangents at pi-halves on sine. Then it should logically make sense to us that since the derivative of sine is cosine, that at pi-halves of cosine, the slope, which is the derivative, is also 0. That's what the investigative part of the paper is saying. That's what the follow-up questions are saying. So how do we know this? Well, we know this because we have horizontal tangents on our graph of sine at pi-halves a. And I'll put that wording up right here. In terms of this graph and its derivative, which variable affects the slope? That. So if you're looking at that, and you're looking at these answers, what variable affects the slope? X or Y? So look at your sine graph up above, right? So are the y values changing going to affect the slope, or are the x values changing going to affect the slope? No, I was going to say we disagree about x's and y's. So I was going to ask you, as the follow-up to that, which variable is in my slope equation? Therefore, x will affect it. Wow. I'm sorry. Hey, at least you answered. Yeah. So algebraically, the y-coordinate does not affect the value of dy dx. Why or why not? Well, it does not because A, it's not in my slope equation, and the slope is either going to go up or down, and it's not going to be affected by the y values. Did you just read the next sentence?
Right there.
Okay. The second reason is the y value that would affect it becomes 0 when you take your derivative. Does the 3 graphs I show you show that? And yeah, you're shaking your head, yeah, right? Like, we can see that from those 3 graphs because if you compare the y values for the slopes, doesn't the slope only change? Like here it's always zeros. Here, if you look at your, I still want to keep moving, please. Okay. Well, if you look here, aren't all 3 slopes the same? So the x value is the same, the y slopes are the same. So that is also part of the reason that y doesn't change it. If the slope at x and y in that same line was different, then both affect it. And that's what we're looking at today. So the slopes are equal at values of x regardless of y. So what it means is all the y's have the same slope for x. All the y's have the same slope for x. According to the differential equation dy dx equals cosine x, which of the slope of the solution curves be when x is 0? So the slopes of the curves should be 1. So go to x equals 0, Does it look like that slope is at 1 on your sine graph? Yeah. Is it positive, like not too steep? So that's what you have to start getting comfortable with today, is you're going to be drawing in little tiny slope lines. So you need to understand, okay, what's a slope of 0 look like? Well, we just saw it. Those are the horizontal tangents. What's a slope of 1 look like? Well, it kind of looks like it's connecting the 2 dots. If it's a slope of 2, then it's going to be a little steeper than that. So just getting comfortable with understanding that. According to the differential equation, dy dx equals cosine x, what should the slope of the solution curves be then when x is pi? So again, you want to find an x value slope, you plug that x value in, you get your answer. In this case, cosine of pi is -1. Cosine of x is an even function, therefore the slope at any point should be the same as the slope as its reflection. How do we see this? So again, it's even, so it's reflected. We should be able to see that within our graph. Okay. So let's talk about real slope fields and how to produce them. We take the ideas explored above, and since we use them to produce it, this is just like an example of what one should look like. So here, if you're looking at this slope field graph, are the slopes at the y's always the same for the slopes at the x's? So like in the cosine graph, all of the y's have the same slope in a column. Are all of the slopes in these y columns the same? No. So what that means is that this graph affects its slopes. So this graph is affected by its slopes. So what we're going to do is I'm actually going to construct the slope field that's up there with you on your paper. So you kind of have an idea of what we're looking for our slope field to look like. And then we're going to actually construct it by hand on your paper. Great. So we're investigating the equation dy dx equals negative xy. So what's the difference from this dy dx that was from our first one? On the first dy dx, it was equal to cosine x. There was no y. Now, this one's dy dx equals negative x over y. So that's why the y's and x's are both going to change. So what we want to do is, and this is the new part for me, we're going to make a dy, a dx, dy, a dy dx table in which we compare the slopes at particular points. I think that's about 5 by 5. We're not going to do all 5 dots because that'll be crazy. But we're going to look at or investigate quite a few of them. So technically what you would do is you would go out, so let's just go, we'll do 5. We'll do -3, -2, -1, 0, 1, 2. And then we're going to compare to the y values. So these are your x's, these are your y's. And we'll do the same thing. This table is going to represent the slopes of the slope field numbers you're going to plug in. So think really easy to start. Anytime y is 0, what do you know about the slope? What do you know when you divide a number by 0? The slope is undefined. So in your table, immediately hit all the y zeros with an undefined. The second thing I like to do in that table is look at when x is 0. So what do you know about 0 divided by a number? So then I hit all my x's being 0. Undefined is more powerful than 0. Undefined is more powerful than 0. So the undefined is going to overpower the 0. That's why I do the undefined first. So I look at my denominator first, look at all the key points there, then I go to the zeros for the numerator. All right. Next, I just start in the top corner. So you're going to have a negative. So this is the x's, right? So it's a negative 3, which means it becomes a divided by a negative 3. So positive 3 divided by negative 3 is negative 4. So you have to take this x and this y and plug them in. So it's negative 2 over negative 3. Nope. A negative 1, which is 1, negative 3. And now the positive and the negative. So all of these will be negative, but then once you get to the positive x's and a negative y, all your answers are going to be positive, and they're same values, right? So this will be 1/3, this will be 2/3, and then technically I ran out of room, but if you did 3, it would be negative, it would be 1. So like I was trying to get my table to keep like that. So that same pattern is going to apply the whole way through. So anytime the x and y values numbers are the same, then their slopes are going to be 1 or negative 1, depending. So in this case, the negative and the negative make this negative 1. Negative and negative make this negative 1. Positive with the negative. The 2 2's also become negative 1. So then conversely, in my table, when you have negative 1 and 1, that's going to be positive 1. And I have negative 2 and 2, positive 1. A negative and a positive here end up making this positive, negative, negative, positive, keep that positive. But do you kind of see the pattern? So I look for patterns as I do the table. You can also just plug in straight across. There's not really like a right or a wrong. So this is always going to be a positive 3 right now. So then positive 3 over negative 1. So then what you would do is on those dots, put these slopes to the best of your abilities at those coordinates. So, Right. So I think some of you have looked at the easy slopes, right? I noticed a few of us put in our zeros and we put in our let's go blue. Undefined. The next really easy slopes to put in are the positives and negatives that are opposites of each other. So I would look at the x values being 0. So where is x 0? X is 0 up and down in the middle. So when x is 0, the slope is 0. So a slope of 0 is a horizontal line. When y is 0, the slope is undefined. A slope undefined is a vertical line. So when y is 0, all of your slopes are straight up and down. So those are the two easiest ones to look at. And then, and again, I know your table goes up to -5, -5. So just go to -3, +3 on your chart. And you would put in a slope that is approximately -1. So that means it's going to be down and almost connecting your two dots. So again, mine doesn't have it because it's way up there. And then you go to -2, +2, and you want to make that line, again, looking like it's pointing at the dot below. So all those diagonal points have that -1, and then conversely, when x is -1 and y is +1, so over here, it's a positive slope. When x is positive and y is negative, you're down here, also positive. Okay. Right. So then I just start filling in all my slopes. So -3 on x, -1 on, or -3 on x at -1. Those are negatives. They might be correct there, but I was in the spot. -1. Actually, I'm not sure if I can do the table. Oh, all right, I have that. Positive one, negative one, is a positive. And then at x being -2 and -2, you're down here, and my slope is -1 when x is -2 and y is -1. It's at -2, so it's just slightly steeper. And then when it's -2 and +1, it's positive and slightly steeper. So you'll notice that my -1 slopes look like this, my -2 and my +2 slopes are just slightly steeper. And there are all of your slopes. So eventually, what shape does it look like all those slope fields are kind of forming? If I were to take them and connect them, so if I started here and I follow the slope, so again, I'm saying all the twos, what does that kind of look like? Find the antiderivative of dy dx equals -x. So go back to this equation. And let's apply yesterday's lesson. So what did we have to do yesterday? We had to say that the y's needed to be with the y's, x's need to be with dx's. So get y dy equals x dx. Keep the negative with the x. I always like to keep like the negative, the number with the x. Antiderivative of y is 1/2 y squared. Antiderivative of -x is -1/2 x squared plus c. How do we feel about that fraction? Not a fan, right? We gotta get rid of the 1/2 on the y. So we're gonna multiply everything by 2. So I get y squared equals -x squared plus c. Add over x squared, I get y squared plus x squared equals c. What's the equation of a circle? X squared plus y squared equals r squared. So is c not acting like my r? So again, if you go back to like this really beautiful little slope field you made, if I make my r or my radius 2, wouldn't that put me here on that circle? So if my radius is 2, what's my c value going to be? 4. So again, if you plugged in or picked the point 2, 0, and you plug that in for x squared plus y squared, 2, 0 means x is 2 squared, y is 0 squared. Do we not end up seeing a radius of 4? See, super cool. Save changes. Don't save, because I didn't really know that on there. I just love that. Alright. So as a follow-up to that, let's look at another much simpler example. And I'm going to show you the way I did it in the past with like a different table. So it says plot the slope field for the differential equation dy dx equals 2y. So what again is different? So cosine x, the last one was negative x over y. This one is 2y. So what isn't changing then? The x values are not part of my slope. Therefore, the only variable affecting it is the y's. So now, in the last one, the x's and y's both changed the slope field, so there was no pattern. Well, in this example, y is the only thing that's going to affect dy dx. So in terms of a table, if I look at my y values, I'm going from 2 to 1, 0, negative 1, negative 2. So again, starting in the top and going over. It doesn't matter what the x's are. So I don't have to do like an x and a y table because the y's are only affecting it. So when y is 2, my slope is 4. When y is 1, my slope is 2. When y is 0, my slope is 0, negative 2, negative 4. So what that means is the x's are useless. The slopes are going to be the same across the rows. Every row has to have an identical slope. So the easiest row is the row when y equals 0. So when y is 0, all of my slope fields are okay. So y is 0 horizontally. When y is 1, all of my slopes are, and that's positive. So whatever slope I put at 1, the slope at 2 needs to be substantially steeper. Right? So like it doesn't, again, the slope is kind of partial to you. I just know whatever I put at 1, what I put at 2 has to be steeper. And then the goal is whatever I put at negative 1 should be like the opposite of what I put at positive 1 because they're opposites. One's positive, one's negative. So I want to take like that same idea, but like flip it. Does that make sense? Okay. As a follow-up to that, it says that suppose you know the point 0, negative 1 is a particular solution on the original problem. So now it's like yesterday and today together. This is my differential. The differential has the IVP, initial value point, 0, negative 1. So go to this graph, go to x being 0, y is negative 1, and you plot that point. So what you want to do is, and this is what's on the AP test, you have to follow the slope lines to graph that point. So you're going to follow the line. So where does this line take me? Takes me up, right? But then what happens when I get to the y-axis? Or, sorry, the x-axis? My slope's 0. What do we call that? We call that a horizontal. So graph has a horizontal asymptote at y equals 0. If you follow this graph down, Again, you're following the slope field. Does that make sense? You kind of follow the lines. So that was example 7, 8. What do you think 9 is? 9 is to do what we did yesterday. So we're going to actually integrate, find our equation, and solve our C value. So dy dx equals 2y. So you get the y's on the left. So that's like 1 over 2y equals dy equals dx times dy equals dx. Now you have a choice. And I am particular to doing it this way. Oftentimes I see students divide both sides by dy and move over the dx, and they put the 2 with the y. What that does is kind of create problems for you once you start doing the ln. So instead of moving my 2, I personally leave the 2 with my dx and only divide by the y. I like to leave the numbers or the constants with the dx's. I think it makes your math easier. I also think it makes you not forget to bring back to x and plus c. So I personally would leave the y. It's not wrong to move it, but I would get ln of y equals 2x plus c. If I were to do this and anti-derive it, that's what I would think is the easiest. How do you get rid of an ln? Because we want to solve for y. Leave both sides. So yesterday, Tessa didn't see this, and maybe it's a little tricky to hear it, and it was kind of on that handout I handed you. Anytime we have an e to the 2x plus c, by technicality, the rule is that if you have a to the m plus n, that's the same as a to the m times a to the n. Because the rule of exponents is that if you have two exponents being multiplied together with like bases, you add the exponents. So in this case, I want to treat that as the multiplication instead of the addition. So it's kind of like saying this is e to the 2x times e to the c. But remember, I told you that anytime I have an c with another number being multiplied, whatever, that c absorbs it. So if you get a problem with an ln and the c is up there in that plus area, what we're going to do is we're going to make our lives easier. We're going to have the e absorb the c, and the c is going to come in front of the e. And that should make sense, and we're going to go back to exponentials in 6-4, which is really where we're going to at the end of this week. Y equals y naught e to the kt is part of that formula, right? It's always y naught in front of the e value or in front of that. That's why it's the e value or the c value. So we have y equals c e to the 2x. In this case, my point that I was given was 0, -1. So that's my x and my y. So you're going to plug those in. So you have -1 equals c e to the 0. Well, you know about anything to the 0 power, it is perfect, 1. So in this case, my c is -1. So my equation is y equals -1 e to the 2x. And again, that should make sense, right? You plug in 0, you get -1. You're down below. Can you ever get a positive value from that? So that's why, again, if you go back to that slope field, does my slope field ever become positive with my blue line drawn in? So the equation we just got, that y equals negative 1 e to the 2x, is this blue line. They go the same. Should have done it in blue. Sorry. This is the line you drew in on your slope. That's the equation that represents that line. So this equation represents the blue line you drew in on your slope field. Okay. Let's do one more slope field. If you like the table, go ahead and do the table. I'm going to try to do the table with you. I'm also going to let this sit here for a minute. So if the table's confusing to you, this is like the way I used to do it. I used to write like X, Y, and put all the ordered pairs as like an ordered pair. Plug that ordered pair in, and then put this down as the slope. Somehow I feel like this is like a lot more chaotic looking than the table. This, the ordered pairs. That's why I said, like, it's really just like, it's a matter of preference. So it doesn't affect me either way. So like, if an ordered pair works for you, write out ordered pairs. So my suggestion would be to start in like the corner. So your first ordered pair would be negative 2, 2. And then you just plug in all of those points to get out your value. So if x is negative 2, I was losing my mind. I was like, I wrote it as 0, but it's not 0. So the zeros are always pretty easy. They're also like the easiest ones to follow. And again, it didn't ask you to antiderive, so you don't have to antiderive. This one would be really gross to antiderive. So we have to add to y after you multiply by dx, and it's just gruesome. Because then you have to back substitute. So this one isn't one we would antiderive. It's just very